I'm Anirudh, and today I'll be taking through my project which I did for the course Machine Learning Foundations for Product Management as a part of Coursera, which the degree is issued by Duke University. So let's get into the introduction of the project. So this project is about building a model to predict electrical energy output of a combined cycle power plant using different feature sets and feature columns that are given, for example, temperature, ambient pressure, relative humidity, exhaust vacuum, to predict the target variable, which is net hourly electric energy output. So for this, we have a dataset given by the Coursera, and then I'll take you through the dataset right now. So this is the data set. It has roughly about 9,800 columns, and the column definition covers temperature in the range of 1 degree to 38 degree, etc. So similarly, we have the ranges given for ambient pressure, relative humidity, exhaust vacuum, and net Harley energy output. So let us get into the approach we've taken to sort of understand how we go about building our model. So first things first, so I have taken this data and then tried to understand what sort of model is required to come up with the predicting the target variable, which is PE in our case. So for this, my approach was to find the correlation value and the scatter plot between each independent variable and the target variable we have. So this led to the following results for me. So what we are largely seeing here is most of them have a linear relationship. For example, AT versus PE has a very strong negative correlation. Versus PE has a strong negative correlation. AP versus PE has a moderate positive correlation. And this is based upon the correlation value that we can interpret in Excel through the correl function that we can use, which gives the correlation coefficient between two data sets. Well, right. So here you can see the scatter plot that we have plotted as well, and the values of the correlations switch between +1 to -1 indicating a perfect negative correlation, +1 indicating a perfect positive correlation. So so the real conclusion that we could make is here is that since P is a continuous variable and relationship with its independent variables are mostly linear, linear regression would be the ideal for our use case rather than a random tree, forest method, or anything else, which sort of explains the complicated relationship between data sets that doesn't have a very predefined relationship between each other. So moving on, let us look into the model test data one. So let me take you through the approach that I've followed. So here on the left side, we have the full data set. Here I have the training data set, which has been randomized and picked up with 80% of the data set used as training data, and then 20% of the data set used as testing data. So I'll get on this coefficients in a bit. So once we ran the data analysis multiple regression model through our training data set, we achieved the following results. So we got a great R square of 0.92, which is great. It means that it is able to explain the variations in the data set up to 92.8%. And we have very low significance F value and a very high F value, which means the null hypothesis can be effectively ignored. So what it essentially means is that our predictions of regression is quite true. And then here you can see that we have various coefficients predicted for each the independent variable we have, and then we have a t-stat value, we have a p-value, which is very, very close to zero, which essentially means that we can reject the null hypothesis of that parameter. And then the confidence level does not include zero, which also is a very reassuring factor that the variables we have used is actually contributing to the model. But I've highlighted the AP value in red because if you could see the coefficient clearly, what does this coefficient generally mean? It means that for each increase of one value in AT, there is a decrease of minus 1.98 value in our target variable, which is P. So that was the coefficient means in the multiple regression. So AP has the least effective value, 0.05 contribution. So I've kept it as red because maybe if you could remove this particular feature and train a model to, maybe that could be even better because the significance of this parameter is less. So this is what we have achieved through our training data set. So applying this model to our test data set and then getting the predictions through the coefficients that are there. Intercept is nothing but if you have all the independent variables 0, what is the value of our target variable? That is what intercept mean. So these are the predictions, and then the next one is this is the prediction, and then this is the absolute error. This is the square of the absolute error, and then I have used since it's linear regression, it's quite useful to use MSE, and then a root mean square error to sort of understand if our model is performing really well. So we have the mean absolute error, which is nothing but the average of all the absolute error we have, mean square error, which is the average of all the squared error that we have, difference between the PE and the predicted PE. And then we have an interesting formula for R squared, which is sort of 1 minus the summation of the all the square error that we have divided by the squared error between PE values and its own average. So R squared comes out to be 0.928, which is again great, which means the model is able to explain the variations up to 92.85 percentage. So it validates that the model has been performing great and it's a very acceptable standard. So the training data affirms it confirms the accuracy of the model generated. So moving on, we have the second model which we have created. Again, we took the full data set and then applied a randomized function, took 80% of the data as to train, 20% of the data to test, and then the results of creating the linear regression on the training data set of the model 2 is here. So we have R square of 0.9271 and the adjusted R, which is very close to R square, which essentially means we don't have any non-functioning parameters in our model. So it very closely reflects that all the parameters we have used are very important. And then we have very high F score, a zero significance F, and then you can see all the p-values are very close to zero, which means the null hypothesis or the contribution of the variables are very significant and we can take it. So we have the confidence levels, a confidence level interval, which does not include zero. And then we have all the coefficients here, which we'll use to now train our data set. So we've took all the coefficients here, and then the intercept is 500, which essentially means if AT is 0, V is 0, RH is 0, our predicted variable is 518. So let's get into our predictions, and then following this similar process, we took the average of all this to calculate R square. We have an absolute error here, and we have squared errors which of that absolute error, and then we have the results of our test data validations. Mean absolute error is the average of all the absolute error. Mean squared error is nothing but the squared error of all the absolute error, and then R square, as I explained, is 1 minus summation of all the squared error upon which is divided by the squared error between the actual p value and its own average. So when we get the R square, we are getting a great value of 93.29 percentage. It is able to explain the variations in the data set, which means the training data, the test data confirms the accuracy of the model generated. Correct me here also, it's not the training data, it's the test data that affirms the accuracy of the model generated. So I'll just make that small change. Yes. So the test data confirms the accuracy of the model generated. So let's get into the comparison and the conclusions of, fine, I have two models, so which is better? Yes. So here we have the conclusion page. So we have the R square, which is pardon me, I'm just using the test data results that we have to compare the models, which is sort of the important thing because we need better predictions from what we have trained in the training data set. So we have a R square of 93.29 in model 2 with excluding the independent variable AP. And then we have almost same mean absolute error, but we have lesser mean squared error. So this mean squared error actually punishes the outliers very highly. So a lesser one, it implies that we have less outliers than the model one. And root mean square is also slightly lesser. So in conclusion, we can conclude that since the accuracy generated to the second model is much better, and through all our validations and all our data, we could go ahead with the conclusion that model 2 with the feature set excluding ambient pressure is better than the model 1, which includes all four parameters for linear multiple regression. So in conclusion, coming back to the interaction set, so in this so the model we have created will use temperature, relative humidity, exhaust vacuum to find the PE value, which is nothing but net Hawley electrical energy output. So thank you folks for seeing through the video. I hope you've understood the concept and you will appreciate the project I've made.